The normal curve was first developed mathematically in 1733 by the French mathematician Abraham de Moivre, but his paper was not discovered until 1924 by Karl Pearson. Instead, it is the German mathematician and physical scientist Carl Friedrich Gauss who is credited with introducing the distribution when he was analyzing the errors he made observing star positions. He reasoned that he was more likely to make small errors than large ones, that he was just as likely to be on one side than the other, and that the larger the error, the less likely. What he came up with is often called the normal distribution, but sometimes called the Gaussian distribution in his honor. Although less frequently acknowledged, the French mathematician and astronomer Pierre-Simon Marquis de Laplace used the normal curve a few years before Gauss in 1783 also to describe the distribution of errors. Hence, occasionally you may hear it referred to as the Laplace-Gaussian distribution. Around the turn of the 20th century, Karl Pearson popularized the term normal as a designation for this distribution. He later recognized that this label is somewhat unfortunate, as he wrote in 1920, "Many years ago I called the Laplace-Gaussian curve the normal curve, which name, while it avoids an international question of priority, has the disadvantage of leading people to believe that all other distributions of frequency are in one sense or another abnormal." Informally, this curve is often called the bell curve due to its bell shape. The normal distribution is the most frequently used statistical distribution. It is employed when computing percentiles and in statistical hypothesis testing. Many physical, biological, and social measurements approximate a normal distribution. For example, the height of all people of a particular race, the length of all dogs of a particular breed, IQ, memory and reading skills of people in a general population. The properties of the normal distribution include its symmetric shape. If folded in half, one side of the curve perfectly mirrors the other. Because it is symmetric, a second property is that the mean is equal to the median is equal to the mode. A third property of the normal distribution is that most of the cases cluster fairly closely to the mean of the population. Specifically, 68% of all cases fall within 1 or -1 standard deviations from the population mean. 95% of all cases fall within plus or minus 2 standard deviation units from the mean. And 99.7% of all cases fall within 3 standard deviation units above or below the mean. If a population is normally distributed, values beyond 3 standard deviation units above or below the mean are very unlikely to occur. There is not just one normal curve. Instead, it is a family of distributions. 2 characteristics used to identify a particular normal distribution are the mean and its standard deviation. We will deal with a special type of normal distribution that has a mean of 0 and a standard deviation of 1. This is referred to as the standard normal curve. The random variable associated with this distribution is referred to as z. Once sample data have been transformed into z-scores, a table that reports the area under the standard normal distribution is used. When doing so, we do not think about the probability of a particular z-score value. Instead, we are interested in the proportion of the area under a normal curve in relationship to 1 or 2 specific z-score values. Because the standard normal curve is a symmetric distribution, 0.5 or half the area under the curve falls above the mean of 0, and 0.5, the other half of the area under the curve, falls below a mean of 0. So the total area under the curve is represented by a value or proportion of 1. What you see now is a typical table that reports the area under the standard normal curve. The diagram toward the middle top of the table illustrates that the area that's reported is the area between the mean of 0 and a z-score value. Now the numbers in the far left margin of the curve indicate a z-score value to the 10th, and the numbers in the top margin of the table are the 100th value of a z-score. The numbers in the middle of the table are the area between a given z-score and the mean of 0. To demonstrate how to use the standard normal curve to find the area, we will work through several types of problems. The first set will ask us to find the area under the standard normal curve between the mean of 0 and a positive z-score value. The first question in this set asks us to find the area under the standard normal curve between the mean and a z-score of 1. Our first step will be to highlight the row that reports a z-score of 1.0, and then to highlight the column that reports the 100th of 0. The number that appears where these highlighted sections intersect is 0.3413, and that's the area between the mean of 0 and 1.00 z-score. To illustrate what this looks like, we draw the normal curve, and we identify the value of 1.00 for a z-score, and we see here that the area between the mean and a z-score of 1.00 is 0.3413. For the second problem, we are to find the area under the standard normal curve between the mean and a z-score of 2.0. Just like before, the first thing we'll do is highlight the row with a z-score of 2.0 and the column with the 100th of 0, and we see that the value where these two highlighted areas intersect is 0.4772. So let's put that on our standard normal curve. And I've placed the value of 2.00 where it would belong on the normal curve, and we see that the area, 0.4772, is quite a bit larger than what we saw with a z-score of 1. The third question asks us to find the area under the standard normal curve between the mean of 0 and a z-score of 3. We highlight again the row that reports a z-score to the 10th, 3.0, and then find the column where the 100th of 0 is reported, and the value where these two highlighted sections intersect is the area between the mean of 0 and a z-score of 3.00. Constructing the normal curve and reporting that z-score value of 3.00, we see the area between the mean of 0 and the z-score of 3.0 is 0.4987. So virtually all of the area above the mean of 0 is contained within the area between 0 and 3.0. That's why when we use a standard normal curve, we say that values beyond 3, while possible, are not very likely. And that is justification for indicating a value beyond 3 as being an outlier. For the next problem, we are to find the area between the mean of 0 and a z-score of 0.08. So we highlight the row that reports a z-score value of 0.0 and highlight the column that reports the z-score to the 100th, 0.08, and we see the value where these two highlighted areas intersect is 0.0319. Reporting the z-score of 0.08, we notice that it's very close to a value of 0.0, and the dark area that represents the proportion of the curve between 0 and 0.08 is only 0.0319. So only about 3% of the curve falls between 0 and 0.08. Item E in this set requires us to find the area under the standard normal curve between the mean of 0 and a z-score of 0.65. So we'll highlight the row that reports a z-score of 0.6 and the column that reports a z-score to the 100th of 0.05. And we see the value where these two highlighted areas intersect is 0.2422. Once again, drawing the normal curve, we place a value of 0.065 for a z-score, and we see that the area between 0 and 0.65 z-score is 0.244 proportion of the curve. So about 24% of the curve will fall between 0 and a z-score of 0.65. For item F, we're asked to find the area between the mean of 0 and a z-score of 1.17. We highlight the row that reports a z-score of 1.1 and the column that reports a value to the 100th of 0.07. Placing this information on the normal curve, we see a value of 1.17 is farther away from a mean of 0 than a value of 0.65 in the previous example, and that the area of the curve between a mean of 0 and a z-score value of 1.17 is 0.3790, or about 38% of the curve. For the last problem in this set, we are to find the area under the standard normal curve between the mean and a z of 2.32. So we highlight the row that reports the z-score of 2.3, and then we highlight the column that reports a z-score to the 100th of 0.02. And we see where these two highlighted areas intersect. That is the area between the mean of 0 and a z-score of 2.32. Going back again to our standard normal curve, we place along the bottom where the value of 2.32 z-score would fall, and the dark area indicates that the proportion of the area under the curve between a mean of 0 and a z-score of 2.32 is 0.4898. So about 49% of the area under the curve. The second set of problems that I demonstrate here ask us to perform the same procedures that we undertook in the first set, the only difference being here that the z-score values are negative values. The first problem in this set asks us to find the area under the standard normal curve between the mean of 0 and a z-score of -1. Now you notice our table for the area under the normal curve does not report negative z-score values. But keep in mind that the standard normal curve is a symmetric distribution. So whatever area falls between a z-score of 0 and +1 will be identical to the area between a mean of 0 and a z-score of -1. So we merely take the absolute value of our z-score to find the appropriate area under the curve. So we'll take our z-score of -1.00 and look up the absolute value of that z-score of 1.00. Highlight the row where a z-score of 1.0 is reported, and then highlight the column that reports the z-score to the 100th of 0. And we'll see the value where these two highlighted areas intersect is 0.3413, which we will now place on a normal curve. A z-score of -1.0 falls to the left of the mean of 0, but the area under the curve between -1 and 0 will always be a positive value. You cannot have negative values for area. And in this case, 0.3413 of the area under the curve falls between a mean of 0 and a z-score of -1.00. For the second problem, we're to find the area between the mean of 0 and a z-score of -2. Again, take the absolute value of -2 for a z-score, and we will look for the row that reports a z of 2.0 and a column that reports the 100th of 0. And the value that's apparent where these two highlighted areas intersect is 0.4772. A z-score value of -2 falls a considerable distance away from the mean of 0, and the area that now is contained in that portion of the curve is 0.4772, or almost 48% of all the area under the curve. For the third problem, we are to find the area under the standard normal curve between the mean of 0 and a z-score of -3.00. Highlight the row that reports a z-score of 3.0 and the column that reports the hundredth of 0. And we'll see where these two highlighted areas intersect is the value of the area between a mean of 0 and a z-score of 3.00. Going back to our figure of the standard normal curve, recall that the z-score we're looking up is a value of -0.300, so it falls far away from the mean of 0 on the negative side of the distribution, and the area between that z-score and a mean of 0 is 0.4987. So almost all the area under the curve below the mean falls between a z-score of -3 and the mean. For the fourth problem in this set, we are to find the area under the standard normal curve between the mean and a z-score of -0.42. Again, looking up the absolute value of our z-score, we highlight the row that reports a z of 0.4, and then the column that reports a z-score to the hundredth, that is 2. And we see the value that appears at the intersection of these two highlighted areas is 0.1628. Drawing our normal curve, we see the z-score of -0.42 falls to the left of the mean of 0, but not very far away. And the dark portion of the curve indicates the region that falls between 0 and -0.42, or 0.1628 proportion of the curve. For the next problem, we're to find the area under the standard normal curve between the mean and a z-score of -0.89. Again, looking up the absolute value of our z-score, we highlight the row of 0.8 and the column of 0.09. And we see the value that appears where these two highlighted sections intersect is 0.3133. Drawing our normal curve, we saw the value of -0.89 falls a little further away from the mean than our previous example, and the darkened portion of the curve indicates that 0.3133 proportion of the curve falls between 0 and a z-score of -0.89, or about 31% of the area under the curve. For the next problem, we are to find the area under the standard normal curve between the mean and a z-score of -1.68. Again, we use the absolute value of our z-score, and we highlight the row that reports a z of 1.6 and the column that reports 0.08 for the hundredth, and the value that appears where these two highlighted areas intersect is 0.4535. Identifying a value of -1.68 falls a fair distance to the left of our mean of 0, and the highlighted area, the darkened portion of the curve, illustrates that 0.4535 proportion of the curve falls between 0 and -1.68, or about 45% of the curve. The last problem we'll work through asks us to find the area under the standard normal curve between the mean and a z-score of -0.224. Taking the absolute value of -2.24, we highlight the row that reports z 2.2 and the column that reports 0.04, and the value that appears at the intersection of these two highlighted areas is our proportion that we will now add to our normal curve. Drawing our normal curve, we see -0.224 falls a good distance to the left or away from the mean of 0, and the area that's darkened that falls between a z-score of -0.224 and 0 is 0.4875. For the third set of problems, we are to find the area under the standard normal curve between two non-zero z-scores. The first problem in this set asks us to find the area under the standard normal curve between a z-score of minus 0.69 and a z-score of 2.51. Recall that the table for the area under the normal curve only reports the information, that is the proportion of the curve, between a mean of 0 and a z-score value. It does not report the area between two non-zero z-scores. So what we will have to do is look up both areas under the curve for each of our z-score values. First, we'll take the z-score of minus 0.69. Taking the absolute value of that z-score, we'll highlight the row that reports a z of 0.6 and the column that reports a z of 900th. And we'll see that the area that falls between the mean of 0 and minus 0.69 is 0.2549. We'll perform the same procedure to look up the area between the mean of 0 and a z-score of 2.51. Highlight the row that reports a z-score of 2.5 and the column that reports the z-score of 100th. And the value that appears where these two highlighted areas intersect is 0.494. Drawing the normal curve, we first will identify where minus 0.69 will fall in the curve, and we'll see that the highlighted area of the proportion of the curve between 0 and minus 0.69 is 0.2549. We now identify where the z-score of 2.51 would fall into the curve, and indicate that the area between the mean of 0 and 2.51 is 0.4940. Now recall what we're asked to find here is the area between minus 0.69 and 2.51. So we merely add those two areas together. So the entire area under the curve between a z-score of minus 0.69 and a z-score of 2.51 is 0.7489. Drawing the normal curve, we first will identify where minus 0.69 will fall in the curve, and we'll see that the highlighted area of the proportion of the curve between 0 and minus 0.69 is 0.2549. We now identify where the z-score of 2.51 would fall into the curve, and indicate that the area between the mean of 0 and 2.51 is 0.4940. Now recall what we're asked to find here is the area between minus 0.69 and 2.51. So we merely add those two areas together. So the entire area under the curve between a z-score of minus 0.69 and a z-score of 2.51 is 0.7489. For the second problem in this set, we are to find the area under the standard normal curve between a z-score of minus 1.29 and a z-score of 1.62. First of all, we'll take the absolute value of minus 1.29 and highlight the row of 1.2 and the column of 900th. And we can see that 0.4015 proportion of the curve falls between the mean of 0 and a z-score of 1.29, or in this case a z-score of minus 1.29. We now highlight the row that reports a z-score of 1.6 and the column of 0.02, and we see that 0.4474 of the curve falls between the mean of 0 and a z-score of 1.62. Placing both z-score values on the curve, we see that minus 1.29 falls below the mean of 0, and the area between 0 and minus 1.29 is 0.4015 proportion. The proportion of the curve that falls between 0 and 1.62 is 0.4474. Adding those two values together to get the total area under the curve between minus 1.29 and 1.62, we see that the total area under the curve between these two z-score values is 0.8489. For the third problem in this set, we are to find the area under the standard normal curve between a z-score of 0.71 and a z-score of 1.64. Looking up the area between the mean and z-score of 0.71, we highlight the row that reports a z-score of 0.7 and the column that reports the z-score of 100th. We then perform the same procedure highlighting the row for the z-score of 1.6 and the column of 0.04. We now place our z-scores of 0.71 and 1.64 in their respective places on the standard normal curve, and we indicate how much of the area falls between the mean of 0 and 0.71 and the mean of 0 and a z-score of 1.64. Now in this case, what's different from what we've done before is that both z-score values fall to the same side, that is to the right of the curve. They both are positive values, so both are above the mean. We're trying to find the area that falls between the z-scores. So what we need to do in this case is take the larger area of 0.4495, subtract from that the smaller area of 0.2611, and we see what is left of 0.1884 is the area that falls between these two positive z-score values. So about 18.8% of the curve falls between a positive 0.71 z-score and a positive 1.64 z-score. The fourth problem is similar to the one we just solved, in that it asks to find the area under the standard normal curve between a z-score of 1.85 and a z-score of 2.91, both positive z-scores. So we highlight the row of 0.18 and the column of 0.05 to find the first area. Then to find the area associated with the second z-score, we highlight the row of 2.9 and the column of 100th. Placing both z-score values onto the normal curve, we see that both fall up towards the upper tail of the standard normal curve. An area of 0.4678 falls between the mean of 0 and a z-score of 1.85, and an area of 0.4982 falls between the mean of 0 and the z-score of 2.91. Again, we're interested in the area between the two z-scores, so since they both are on the same side of the mean, we will subtract the smaller value from the larger area. So 0.4982 minus 0.4678 results in a proportion of 0.0304. So only 3% of the area under the curve falls between these two positive z-score values. The next two problems in this set require a similar procedure that we just performed, but this time both z-score values fall to the left of the mean of 0, as they both are negative values. As we have done previously, we'll look up the absolute values of the z-scores in this problem that are reported on a table. Again, we'll look up in a table the absolute values of these z-scores. So first of all, we'll find the row with the z-score of 0.9 and the column of 0.09. We then will look up the z-score of 0.5 and the column of 0.06. Identifying where these z-score values fall, since they both are negative, they will fall below or to the left of our mean of 0. And we see the area between 0 and minus 0.99 z-score is 0.3389, and the area between 0 and minus 0.56 is 0.2123. Since both z-scores fall on the same side of the curve, we will subtract the smaller area from the larger area. 0.3389 minus 0.2123 equals 0.1266. So the area that falls between a z-score of minus 0.99 and minus 0.56 is 0.1266. For this next problem, we have to find the area under the standard normal curve between a z-score of minus 1.91 and a z-score of minus 0.85. We'll take the absolute value of each of these z-scores and find the appropriate proportions from our normal table. So we first highlight the row that reports a z-score of 1.9 and the column that reports a z-score of 100th. And then we find the row of a z-score of 0.8 and the column that reports the z-score to the 500th. Placing both z-score values to the left of our mean since they are negative, but we report the area as positive because area always is positive, cannot be negative. We see that 0.4719 proportion of the curve falls between the mean of 0, z-score of minus 1.91, and we see that 0.3023 proportion of the curve falls between the mean of 0 and a z-score of minus 0.85. Because we're interested in the area between the two z-scores, and they both fall on the same side of the curve, we'll subtract the smaller area from the larger area. So 0.4719 minus 0.3023 indicates that the proportion of the curve that falls between a z-score of minus 1.91 and 0.85 is 0.1696, or about 17% of the curve. For item G, we are to find the area under the standard normal curve between a z-score of minus 1.00 and a z-score of 1.00. Because the absolute value of minus 1.00 is 1.00, we just have to look up one z-score value in the curve. So we highlight the row that reports a z-score of 1.0 and the column that reports a z-score out to the 0/100th, and we see that the value is 0.3413. Placing both z-score values onto our normal curve, we see that 0.3413 area under the curve falls between 0 and minus 1 z-score, and 0.3413 area under the curve falls between 0 and plus 1 z-score. We add those two areas together, and we see that the total area under the curve that falls between minus 1 and 1 z-scores is 0.862, or about 86% of the area under the curve. And this is where we get from the empirical rule the figure, or the estimate, that 86% of all scores will fall between 1 and minus 1 standard deviations from the mean. For item H, we find the area between minus 2 and plus 2 z-score units, and again, because minus 2 is the same, and because the absolute value of minus 2 is 2, we again look up only one z-score value. So we highlight the row that reports z-score of 2.0 and the column that reports 0/100th, and we see the value of 0.4772. Placing both z-score values on the normal curve, we see that 0.4772 proportion of the curve falls between the mean of 0 and a z-score of minus 2, and the same proportion of the curve falls between the mean of 0 and plus 2. Because both of our z-scores are on opposite sides of the curve, we simply add those two values together, and we end up with the area between 2.0 and minus 2.0 is 0.9544 proportion of the curve. And this is where we get, from the empirical rule, the estimate that about 95% of all cases in the standard normal curve will fall between minus 2 and 2 standard deviation units. For the last problem in this set, we are to find the area under the standard normal curve between a z-score of minus 3 and a z-score of 3. Looking up a z-score of 3.0, we see that the area between a mean of 0 and a z-score of 3.0 is 0.4987. Placing both z-score values onto our standard normal curve, we see that 0.4987 proportion of the curve falls between the mean of 0 and a z-score of minus 3, and 0.4987 proportion of the curve falls between a mean of 0 and a standard and a z-score of 3. Because these z-scores are on opposite sides of the curve, we add these two areas together, and we see that the proportion of the curve that falls between minus 3 and 3 z-score values is 0.9974. And this is where we get from the empirical rule that 99.7% of the area under the curve falls within 3 standard deviations of the mean. In this last section to the tutorial, we will focus on finding the area under a curve that falls below a particular z-score value. That is, the entire area that is to the left of a given z-score. Up until now, we focused on finding the area between a given z-score and the mean of a standard normal distribution of 0, or finding the area between two z-score values. But there are times that we will want to know how much area under the curve falls below or to the left of a given z-score. That is, the entire area to the left of a z-score. This is useful for when we're computing percentiles. What we see here in the screen before us are 5 different z-scores that we will use as examples to answer the question, how much area of the curve falls to the left below this particular z-score value. For this first example, we will answer the question, what is the total area under the standard normal curve that falls below a z-score of 1.92? We will begin finding this area the same way that we've done before in the previous examples, by asking what is the area that falls between the mean of 0 and the z-score of 1.92. So we will turn then to our standard normal curve, highlight the row 1.9, add 2 100ths to that, so now we also highlight the column of 0.02, and we see those two intersect at the value of 0.4726. So 0.4726 proportion of the entire area under the curve falls between the mean of 0 and a z-score of 1.92. We now turn to the graph of our standard normal distribution and identify along the base of the graph the value of 1.92 for our z-score. And we indicate here then that 0.4726 of the area under the curve falls between that z-score of 1.92 and the mean of the standard normal distribution of 0. But this is only part of the answer. We were asked to find the total area to the left or below a z-score value. And what we found so far is only that part of the curve that falls between the mean of 0 and a z-score of 1.92. We also, though, need to include the area under the curve that falls below the mean of 0. Going back to the assumptions of a standard normal distribution that is symmetrical, we know that 1/2 of the curve falls below the mean of 0 and 1/2 falls above the mean of 0. So to find the entire area below a value of 1.92 for a z-score, we add 0.5000, which is the area that falls below the mean of 0, to 0.4726, which is the area that falls between the mean of the standard normal curve of 0.00 and our z-score of 1.92. So the result is 0.9726 of the area under the standard normal curve falls below a z-score of 1.92. For the second example, we are asked to find the total area under the standard normal curve below a z-score of 0.49. Turning back to the table for the area under the standard normal distribution, we will first of all highlight the row of 0.4 and then add 9 100ths to that, so we'll highlight then the very last column of 0.09. And we see where those two areas intersect at a value of 0.1879. So 0.1879 area under the curve falls between a z-score value of 0.49 and the mean of 0. Placing the z-score value of 0.49 at the base of our graph of the normal curve, we highlight then the area between the mean of 0 and a z-score of 0.49, and we see that 0.1879 area to the curve falls between those two values. But keep in mind we're asked to find the total area under the curve below a z-score of 0.49. So we then add to that area of 0.1879 the total area that falls below the mean of 0, which is 0.5. So we end up with then, by adding those two areas together, 0.6879 area under the curve falls to the left or to below a z-score of 0.49. For the third example, we will find the total area under the standard normal curve below a z-score of 0.000. Now this is pretty easy, and I'm sure most of you have already figured out what the answer is without even having to go to the area under the curve for a standard normal distribution. But let's go through the same process we've done up till now. So we'll highlight 0.0 in the very first row and add 0.01 to that. So we highlight then the first column as well, and we notice there that 0.0000 area under the curve falls between the mean of 0 and a z-score of 0, which of course we would expect, given that 0 is the mean. So all we need to do then is to ask the question, how much area under the curve falls below a z-score of 0, or the mean of 0? And of course, the entire area to the left, or 0.5000, half of the curve, falls below a z-score of 0.00, which is the mean for a distribution. So the total area under the curve below a z-score of 0.00 is 0.5000, half of the curve. For example number 4, we're asked to find the total area under the standard normal curve below a z-score of minus 0.23. So for these last two examples, we'll be working with z-scores that fall to the left or below the mean. Just as we've done before, we'll take the absolute value of minus 0.23 and go back to our area under the curve for the standard normal distribution, our table. Highlight the row of 0.2, add 0.03 to that, so we'll highlight now the column of 0.03, and we see then that those two areas intersect at a value of 0.0910. So 0.0910 area under the curve falls between the mean of 0 and a z-score of minus 0.23. Plotting the value of minus 0.23 at the base of our standard normal distribution for a z-score of minus 0.23, we now have highlighted or indicated that 0.0910 area under the curve falls between that z-score and a mean of 0. But keep in mind, what we're asked to find is not the area between 0 and a z-score of minus 0.23, but instead the area below minus 0.23. Well, our standard normal curve doesn't tell us that, so we have to then use our understanding of the normal curve to find that value from the information we have. We know that the entire area below the mean of 0 is 0.5000, half of the curve. So we'll subtract from that the area that falls above the value of minus 0.23 and 0 for the mean. So we'll take 0.5000 and subtract from that 0.0910, and that results in a value of 0.4090, which indicates the area under the curve below a z-score of minus 0.23. For this last example, we're asked to find the area below a z-score of minus 2.53. Again, we'll take the absolute value of minus 2.53 and use that to find the area between the mean of 0 and a z-score of minus 2.53. So we look up 2.5 and highlight that row of our table for area under the normal curve, and then we add to that 0.03 or 3/100ths and highlight the column that has a heading of 0.03. And we see now those two rectangles intersect at the value of 0.4943. So 0.4943 area under the curve falls between a mean of 0 and a z-score of minus 2.53. Turning back to our graph for the standard normal distribution, we identify the value of minus 2.53 at the base of our distribution to the left of the mean of 0, and you see it falls well down towards the tail of our normal curve to the left. And we indicate then that the area of 0.4943 falls between the mean of 0 and a z-score of minus 2.53. But keep in mind, we're asked to find the area to the left, or below a value of minus 2.53. So that is the area that's not contained then between the mean and a z-score of minus 2.53. So again, remembering that the entire area under the normal curve to the left of a mean of 0 is 0.5. We then will subtract 0.4943 area under the curve, and that results then in a value of 0.0057. So 0.0057 area under the curve falls below the value of a z-score of minus 2.53.